Hello, everyone. So my name is Jing Ho. I'm a product engineer in Questa Formal team and mentor a Siemens business. I have been working in formal verification field for more than 12 years, 8 years as CAE at Synopsys, supporting Synopsys Formal 2, and 4 years as formal specialist and product engineer and mentor, supporting Questa Formal tools. I got my PhD in formal verification from University of Montreal, Canada. Welcome to DVCon Europe 2020 and this presentation on how to verify encoder and decoder designs using formal verification. This is the agenda for this presentation. The first session is introduction. Then I will go through an example using BCH encoder and decoder design from the Opencore website to show how to verify encoder and decoder designs using two different formal verification methods, property checking and sequential logic equivalence checking. The last session is conclusions. Introduction. For fully verifying encoder and decoder design, we have to consider all possible data come into the design. For the design that can correct random faults, we have to consider all possible random faults. Traditionally, people are using simulation to verify encoder and decoder circuits. They have to write lengthy simulation test benches for generating input vectors, which can be time-consuming. No matter how good the test benches are, they're not able to cover all input vectors within reasonable time. Considering the designs that can correct random faults, it is even harder for simulation to cover all errors happening at any bit and any random time. The traditional simulation method is not sufficient for verifying encoder and decoder designs. In this presentation, I will introduce two formal verification methods, property checking and sequential logic equivalence checking, that can exhaustively verify the functions of encoder and decoder designs. Formal verification can automatically consider all possible values for inputs and undriven wires. I will introduce how to use undriven wire for injecting random faults in next session. To demonstrate the two methods, I will use BCH encoder and decoder design from Opencore website. This design can fix and detect 1-bit and 2-bit random faults injected to the transmission line DSYN and DDIN. So these two signals. So the design, the output signal should be equal to the DIN. That means the design can correct the errors. And the error detected signal should be 1 when error is injected to either the DIN or the DSYN, so any bit of them, but less than 2 bits. Verifying BCH design using property checking. This is a property checking flow. To run the property checking tools, the user provides RTL files and assertions. The RTL files should be synthesizable, and the prop check will do analysis. And to prove the properties, if they are true, or find counterexamples to violate the properties and show the counterexamples in wave view. For verifying the BCH design, we have to list all the functions of BCH design first, then translate them to executable properties. The first function, when there is no error, dout should be the same as din, and error detected should be 0. The second function, when 1-bit or 2-bit random errors are happening on the lines to DC inputs, the errors can be detected, and the error detected output should be 1. The third function, when 1-bit or 2-bit random errors are happening on the lines to DC inputs, the errors can be corrected. and the dout should be the same as din. Inserting random faults. One important part of verifying the design is to cover all random errors happening on the transmission lines from the encoder to the decoder. Formal tools have a unique feature that they can automatically drive random values to free inputs or undriven wires, and also consider all values for them at once. We can use this unique feature to insert random errors. First, we needed to define an undriven wire foo. We're using Quest formal tools. We can use a tool directive to define this wire instead of define it in the RTL. We were using the tool directive netlist cut point to insert random errors. This picture shows the behavior of netlist cut point. When the condition is true, the design signal is cut and driven by user-defined expression. When the condition is false, the design signal is not cut and it is driven by the original design logic. Let's look at the file insert error start do. The for loop considers every bit of the transmission lines from the encoder to the decoder. When a bit of foo is 1, a corresponding transmission line is injected error by driving by the opposite value of the original signal. When the I is less than data width, the error is injected to the d_din signal. Otherwise, the error is injected to the d_sin signal. So each bit of foo controls the error injection. Verifying BCH design with Questa prop check. This is a script to run Questa prop check. The vlog directive compiles the RTL source file. QVerify is a shell command to run Questa applications. The do insert _ error start do reads in the file for inserting random faults. Formal compile builds the formal model, and formal verify runs formal analysis. You can see the script is very simple and easy to create. And here is the verification result. We can see the runtime is fast. Only 20 seconds, all 3 checkers have been proven. That means the design behaves as specified. Sanity waveforms. Questa prop check can find the stimulus sequence that activates the checking logic for properties and show the waveforms that is called the sanity waveforms. This example shows the sanity waveforms of the searching check error detection. The DSYN signal connects the encoder ESYN to the decoder ECC_I. And we can see here the ESYN is 0, but the DSYN is C0. We can see 2-bit errors are injected to the DSYN signal. When the error injected, but we can see the error detected signal can detect the error. It's 1, so that's good. The design detects the error. We can see the dout signal is 0, still equal to the din, so the design can correct the errors. From the waveform, we can see the foo signal. Foo is the undriven wire we introduced to control the error injection. We can see foo here is C00000. And we can see the 2-bit has 1 in foo. Then the corresponding DSYN 2-bit also injected the error. So you can see that's why the DSYN is different from the ESYN because they're 2-bit error injected. From here, we can see the dout equal to the din, so the design corrects the error. The design works as expected. The schematic view also clearly shows 2-bit errors injected to the transmission line from ENC to DEC. And we can see the error detected signal is 1, detected error, and also the dout is 0, still equivalent to the din, so the design corrects the error. From the BCH example, we can see that property checking can exhaustively verify the encoder and decoder design with a simple step. Now let's look at the formal verification method, SLEC. SLEC verifies the functional equivalence of two designs. The user provides two designs. Most SLEC tools can automatically map and tie name matching inputs of the two designs, map name matching outputs, and verify their equivalence. SLEC is using formal analysis that automatically considers all possible values for inputs and undriven wires. After run, SLEC either proves the equivalence of signal pairs or find counterexamples to show their non-equivalence. Verifying BCH design using SLEC. We provide two BCH design versions to SLEC. The version spec is a original BCH design without faults. The version info is the BCH design with random faults. We insert random faults to the info version in a way similar to what we did for running property checking. For the BCH design, SLEC automatically maps and ties DIN and drive them the same, and also automatically map dout and error detected as verification target. To completely verify the functions of BCH, the default mapping targets are not enough. We have to verify that dout in the input version with fault injected is equal to the din, and also we needed to verify the error detected equals to 0 for the spec version without faults and equal to 1 for the input version with faults. Verifying BCH design with Questa SLEC. Here is a script to run Questa SLEC to verify the BCH design. Vlog compiles the RTL files. QVerify is the shell command to run Questa applications. SLEC configure defines the two versions of the design, spec and info. Netlist wire defines the signals of constant 0 and 1 respectively, and the do inject error start do reading the file that injects random faults to info version. SLEC map defines the three verification targets mentioned in the previous slide, that is mapping info dout to din, and spec error detected to constant 0 and info error detected to constant 1. For the example, you can see the setup is simple and fast. Inserting random faults. The code for injecting random faults to info version is similar to the previous example for property checking. We use a netlist wire to define the free variable foo and using foo to control the error injection. Here we have a constraint to control the random faults to be 1 bit or 2 bits, such that the input-output error detected should be equal to constant 1. The verification results with Questa SLEC. From the screenshot, we can see that the runtime is fast, only 7 seconds to prove the equivalence of 4 targets, and find the counterexample to show non-equivalence of 1 target. The proofs are for all compilations of random din, 1-bit or 2-bit errors. The proofs are exhaustive. Only spec error detected and info error detected is not equivalent, since SPEC has no injected fault and its error detected is 0, but input has injected error and its error detected signal is 1. Even though input has random 1-bit or 2-bit errors, input dout is equivalent to SPEC dout and din, which means the design can correct the errors. Input error detected is proven to be constant 1, and the SPEC error detected is 0 because SPEC version has no error injected. From the result, we can see that SLEC has completely verified ECH functions. Here is a counterexample of the target of SPEC error detected and input error detected. And from the wave tab and the source tab, we can see the DSIN is 1A4 in SPEC side, but 1B4 in input side. We can see 1-bit error is injected to the input side. And we can see the error detected is 1, so the design detects the error. And from the waveform, we can see the input dout equal to the SPEC dout also equal to the din. So we can see the design can correct the errors. Here the random random variable flow gets this 11000, so it injected the associated bit of the input DSIN signal. Conclusions. Both property checking and SLEC can exhaustively verify BCH encoder and decoder design. But the two methods use different ways to do it. Property checking verifies assertions against the design, while SLEC verifies the equivalency between the versions with without injected faults. To run property checking, the user needs to provide assertions representing the functions of the design. To run SLEC, the user doesn't have to write SV assertions, but may define mappings. Since formal algorithms consider all possible inputs and random faults, both property checking and SLEC can exhaustively prove the design functions. However, simulation is lack of this capability and cannot exhaustively prove design functions. From the design, we can see the setup is easy and runtime is fast for the two formal methods, while simulation test benches take much more time to write. Formal replication methods, property checking and SLEC, can be applied to other encoder and decoder designs. This concludes the presentation. Thank you. Any questions?
Thank you, Jim. Do you have any questions? So I guess we have one question from Katarina. How large could be the design for the SLEC method? So a number of flip-flops. You can see the questions also in the chat.
Yeah, so, okay. It's really depends on the design itself. We don't have like a concrete data for that. You can handle many like a big size design if the two designs have limited differences, and also if the design doesn't have complicated mathematical operations, multipliers, those kinds of things, then the SLEC can handle really big design, really big one. But if the design has very complicated mathematical operations, big memories, those are bad for formal, not only for SLEC, it's bad for all formal methods. Then the size could be smaller. And also depends on the two designs. If the two designs are very different, change a lot, all the structures changed, then the tool cannot find mappings automatically, then the capacity, the handling capacity could be smaller. So it really depends on the design itself.
Okay, so similar question from Curtis: how scalable is the method in terms of property runtimes? For example, when data in is 256 bits wide and the designer has to detect and correct all the 3-bit errors.
Say again, the question.
You can see also in the
That's-
chat. So the similar
where's
question from in the
let's see
chat. So there is also, if you when you share your presentation, you have one option is the chat, and then you can see also the questions.
So where is the chat? Wait a minute. So
Basically, the question is how scalable is the method in terms of property runtimes? For example, when data in is 256 bits wide and the designer has to detect and correct all 3-bit errors.
for this design, for this example, the BCH only corrects to 2-bit errors, but the 2-bit error can be in any place in the the data lines and also the ECC output, the parity lines. It can be on any bit, but the total errors is less or equal to 2 for the BCH design, and the tool can correct, can find, can verify them.
So
it's not a straight bit.
data wide, the number of bits for the data and the data in is not a issue. So if you have 256 bits, so it's not an issue for this method.
It depends on the. For this one, I run just using the default because I copy the design BCH from the Opencore. I just using the default setting. It's the data is not big. The data weight is not big. Yeah, I didn't try the like 250 weights, whatever. So I just yeah, for this BCH design, yeah, the data, the result is using the BCH from the. I haven't tried anything because this design, yeah, is not using 250 bit. And I said it depends on the design, the logic. So it's really, you have to try it in that formal, you have to try it. You will know if you can handle this design or not. So, and depends on the design, the logic there. So yeah, if the design don't have like a complex operators, multipliers, just the data transport or whatever, so then it can handle big ones. But if you have very complicated mathematical operations, there probably the big data then could cause problem. So before you run it, you don't know for sure. Yeah.
Okay. So there is also a comment from Airi that data wide has effect on the number of injections to do, but in SLEC, so you can also do all injection at once. Is it correct?
Yes, that's yes, the formal algorithm consider all the inputs and also the undriven wire, all combinations at once. Yeah.
Okay.
That's the beauty. That's the beauty of a formal verification.
Yeah.
It's a completely different technology from simulation. So.
Yeah. So another question from Rizwana. So what compilers can this tool support? So it's basically VHDL or system Verilog or what else?
Yeah. So we support Questa formal tools support VHDL, Verilog, synthesizable. Yeah. So the version of Verilog's VHDL, and if the properties you can write in SV or whatever the RTL, or you using PSL or using assertion libraries. So yeah.
Okay. Your main scope here was sorry.
And for the methods itself, I'm talking about the two different formal methods to do the verification. Yeah, so you can use definitely you can use different vendors to do the probably the similar thing. Yeah, but for Questa for Mozo, we are using the Questa side of the tools. So the compiler, so I'm using for generating the table is using Questa tool. So the Vlog is the same common compiler among across the Questa tools. Questa simulation also using Vlog to compile the RTL and then the formal stuff. So the results is from the Questa tool.
Also another two questions. So this method is only can be used only for Questa tools. I guess you answered not, no? So can also use different tools. The same
Yes.
can you reuse the same approach?
Yes.
And another question was, will your method work to verify encoder only? So the scope here was encoder, decoder modules, but this can be also used for different types of designs or not?
Yeah, because for this encoder and decoder, the best way is to combine the encoder and decoder together. Then you don't have to ready to know the algorithms of the encoder to actually verify the encoder individually. If you only verify the encoder, you have to basically, it's hard. Basically, in the prop check, you needed to write your assertions to represent an algorithm in the encoder. So then it's not good. So when you verify encoder, decoder, better to combine them together, then your assertions becomes very easy for the prop check. And also your SLEC is also very easy. You don't care about the algorithm itself. For the property I already listed, you only show the big pictures of the circuit. Yeah, if it can correct errors, if it can detect errors, you don't have to go to the detail of the algorithm when you add encoder decoder together. And for SLEC, it's the similar thing. So you want to just say, okay, if the complete design can detect it or not detect, then you just check the output. So for encoder decoder, my suggestion is to verify them together. So if you separate them, it's not good.
Yeah. And last question, this approach is also applicable for fault injection in the scope of ISO 26262. Yeah.
Yes, that's the perfect application using SLEC to do the fault injection. And a lot of companies right now are using SLEC to do the fault injection to get the numbers to satisfy the ISO 26262. The SLEC is a perfect one because we can random inject errors, and then in simulation it's hard. It's hard to get all the error injected, but SLEC is consider all errors because we're using the undriven wire to control it. It's completely random errors, and also cover all possibilities. So that's the best using SLEC. And also for SLEC, usually because when doing the fault injection, you have the same design, most cases, and the only injected like the example I showed, just the same design, but one version you injected the error and compare the one without injection error, and you can see. And for the we have in Mentor, we have also the tool to optimize to do this.
Yeah. Okay. So thank you very much, Jim. So if other questions, please just approach Jim in another virtual session. So now, thank you very much again, Jim. So go to the next